Hi and welcome to this Leaving Cert Higher Level Applied Maths video, and in this video we're looking at second order inhomogeneous difference equations. So in this video we're going to solve some second order inhomogeneous difference equations, and we're going to explore the link between the second order homogeneous and inhomogeneous difference equations, so where we see exam questions that work with both. So this video is only suitable for higher levels because this topic is not examined at ordinary level. If you want to revise second order homogeneous difference equations before you watch this video, I've linked that video in the description below. So our first step in being able to solve a second order inhomogeneous difference equation is actually identifying. So what does it look like? So it can be in any one of these three forms, and there's even some more different forms we could see. But basically, if you look at each of what we have here, on the left, we have what we would think of as our traditional second order homogeneous difference equation. But on the right, instead of it being equal to 0, like we're used to for homogeneous, we have a function, and that's a function of n. So that first one there is an exponential, the next one is linear, and the last one, just see that's a constant. So when we solve these inhomogeneous, we're getting two different solutions and effectively putting them together. So we have a particular solution and a complementary solution. The complementary solution is the one that we're already used to when we work with the homogeneous difference equation. The particular solution has got to do with that function that we can see on that right-hand side. So let's look at the steps that we need to solve a second order inhomogeneous difference equation. So that is one which can be generalized in this form. We're going to see an n plus 2, an n plus 1, and an n. Now, I say we're going to see, we don't necessarily need to see all three, but what we will be looking for is a difference of 2 in those subscripts. So you'll want to see an n plus 2 and an n. And that should in turn equal to a function, so f of n. And that function could be linear, could be quadratic, it could be a constant, or it could be exponential. So step one, we're going to basically separate out the what will be a homogeneous difference equation and put all those terms on the left, and then we leave the function itself on the right. So in this case, we're looking at our UN terms. We see these letters change depending on what the question is about. So for example, if it was population, they might be PNs and so on. So you want all of them to the left, and we put every other term to the right, and that right-hand side then becomes our function. So we're going to solve to find the particular solution using the table. So the particular solution is basically linked to that function on the right-hand side. If we have a quadratic, then our particular solution will be quadratic. If we have a linear, our particular solution will be linear. So I'll give that table on the next page. So once you have that particular solution, we then solve the homogeneous difference equation. So this is the one where we make the corresponding characteristic quadratic equation, which will be x squared plus something x plus a constant equals 0, and we get those roots. Depending on the roots, then we're going to use the difference equation either 1 or 2. So there are two formulas. So we have our different root theorem where we have two different roots, alpha and beta, and then we have our double root theorem where we're getting a double root. So we have our two answers, but they're both the same. Once you have both solutions, the complementary and the particular, we're going to create a solution for UN that basically puts the two together. So it's going to be the complementary solution plus the particular solution. Step 5, we're going to sub our values of n into this UN and solve simultaneously. And then we're going to write down our final solution for UN. So I like to do the particular solution first because often if we start with the complementary, that's the bit students are slightly more familiar with, and then they kind of maybe give up. If you're in an exam situation, absolutely do it in whatever order you prefer. So this is what the particular solution looks like. So if we have a constant on the right-hand side, so if that function is constant, our answer is going to be a constant. If we have a linear, then on the right-hand side, it will also be linear. So make sure that you have some version of a linear. I say bn plus c, you could write that as an plus b. The letters here don't really matter. What matters is that you have a linear. If you have a quadratic function, then we have a quadratic particular solution. And just note that even in the terms of a quadratic, you might just have like an n squared. That's still quadratic. It doesn't need to be a quadratic trinomial. However, our particular solution will always be a quadratic trinomial. We're going to at least test to make sure that we can get values for a, b, and c. Same with linear. If you had 3n, that is itself linear, even though there's no constant. But when we put in the particular solution, we want to account for that constant. The only exception to this is when we deal with exponentials. If you have an exponential without a constant, then your answer will be an exponential without the constant. So that's something with b to the power of n. Notice how these b's are the same. So that b, which I've used stands for base, is the same. So if that was a 2 to a power, our answer is going to be 2 to the power. And with the exponential, if there is a constant, then we do need our constant in the answer. Now, if you always include the constant, if you find that easier, that's perfect. You'll just get a c equal to 0 for the exponential without a constant. So if you find it easier to learn 4 lines instead of 5 lines, that's absolutely fine. So just be aware constants must go in for the constant, linear, and quadratic. But for the exponential, we can think of it as if the exponential doesn't have a constant, then we don't need to put in a constant. If the exponential does have a constant, then we do need a constant. Okay, so let's take a look at example 1. We're going to solve the second order inhomogeneous difference equation, and we're going to have a linear particular function. So I'm just highlighting that now. We're going to test we're going to try a few different examples with different particular functions and particular solutions, so you can see how all of them will look. So the question is to solve this inhomogeneous difference equation. So the first step is to get all our UN terms on one side and all of the other terms on the right. So that's already there. So we can clearly see here that this is a linear. So this means for our particular solution, we are also going to have a linear. It's really important you're able to identify those functions. So our function f of n is going to be a linear. I like to write my linear as bn plus c because then my constant is c, but again, you can use whatever letters you want for that. So my particular solution is going to be in the form f of n equals bn plus c. And we're going to be subbing in for all the UN terms. So effectively what we're doing here is we're saying, okay, imagine if all those UN terms were instead written as a function, what would that function be? So I'm going to work out here just to kind of, I suppose, give you a better chance, because sometimes when students plug all this in together, there's a lot that can go wrong, especially as we get into harder particular solutions. So what I'm doing here is everywhere there is an n in my function, I'm plugging in an n. So for example, in the second one, we're plugging in n plus 1, so I'm plugging in n plus 1. This one, we're plugging in n plus 2, so that's going to be an n plus 2. So that's b times n plus 2 plus c, and I'm going to multiply that out before I bring it over, because it's going to make my life a little bit easier. So once I have all that work done, you don't have to do this work separately. This can all be done during the substitution phase. We have un plus 2 minus 6, un plus 1 plus 9, un equals 8n plus 12. So what we're effectively doing is saying if each of those un plus 1 and n plus 2 and n were functions, what would they be? So this, we're going to basically plug in f of n plus 2. Then we have minus 6, and instead of this, we're going to plug in f of n plus 1. Then we have plus 9, and this becomes f of n, and then the right-hand side doesn't change. That stays the same. So instead of fn plus 2, we're going to do bn plus 2b plus c minus 6 times. Instead of f of n plus 1, we have bn plus b plus c plus 9 bn plus c equals 8n plus 12. So what we effectively create here is an identity. So an identity is an equation where we don't care about solving for the variable. So I'm not looking for a value of n. I'm looking for the coefficients that are missing. So this is sometimes called unknown coefficients or missing coefficients. So all I want to do is figure out what does B stand for and what does C stand for. So let's do a little bit of expanding and then let's see where we can go with this. So we have 2B plus C minus 6BN minus 6B minus 6C plus 9BN plus 9C, and that equals 8N plus 12. So we can do a little bit of cleanup. So I have a BN, a minus 6BN, and a 9BN. So that's going to give me 4BN. I also have a 2B, a minus 6B, and I think that's it for my B's. So that's going to give me minus 4B. And we also have a C, a minus 6C plus 9C, and that gives us plus 4C, and that equals 8N plus 12. So what you should be able to see now is that if we talk about just the n terms, we know that the n terms have to equate. So that means 4bn has to equal 8n. Ignore those n's, we don't care about them, and that means b must equal 2. So then when we come along, we say, okay, I say the non-n terms. These are effectively the constants, but often we can get confused with that idea of constants and letters. So non-n terms, a bit clearer. We have minus 4b plus 4c equals 12, but we know that b is 2. So I'll just make it clear, a bit of space. So it's minus 4 times 2 plus 4c is equal to 12. That's minus 8 plus 4c equals 12. So 4c equals 20 and c equals 5. So what that means is we now have our particular solution. Fn is equal to Bn, which, sorry, we worked out B as 2n plus C, and that's going to be plus 5. So that's our particular solution. I like to do that first. I like to get that out of the way, and then we can do the nice part. So then the question is effectively getting easier as we keep going. Okay, so I've just cleared off to give us a little bit of space. So now our focus is going to be on getting the complementary solution. I like to label these as we go. You can, it's really only for you if you do. And that's going to be looking at the left-hand side, but equal to 0. So we're back to our homogeneous difference equation. So our characteristic quadratic equation is x squared minus 6x plus 9 equals 0. This actually is a perfect square, which means we're only going to get one distinct root, and that is x is 3. And that's my alpha. That means when we're working with this, the theorem we're working with, Tn is equal to L alpha to the power of n plus m n alpha to the power of n. So let's sub that in. So Tn equals L 3 to the power of n plus m n 3 to the power of n. Now, I did actually use Tn there on purpose because this is just a complementary solution. So what that means for us is when we want to actually get our answer for un, we need to bring that part complementary plus the particular, which is written above. And now that's my answer for un. So rather than using my un there, I kind of keep that notation of my theorem, which reminds me that actually that's not going to be my final answer. It's at this point here then that we do our substitution. So let's do our u0. That's going to be L3 to the power of 0 plus m0, 3 power of 0 plus 2, 0 plus 5 equals 6. So anything multiplied by 0 is gone. Anything to the power of 0 is 1. So that's L plus 5 equals 6, which means L equals 1. U1 then is L 3 to the power of 1 plus M times 1 times 3 to the power of 1 plus 2 times 1 plus 5, and that all equals 16. We also know L is 1, so this is just going to give me 3 plus 3M plus 2 plus 5 equals 16. So 3M gives us 10, so that's going to equal 6, and M equals 2. So our final answer for UN is going to be L, which is 1, 3 to the power of N plus M. All right, let's plug in M, 2N times 3 to the power of N plus 2N plus 5. If you want to do some cleanup, we can absolutely drop that one. But otherwise, it's as cleaned up as we can go. Bear in mind, BIMDAS, you have to do indice work before you do any multiplication. So often, the cleanup you think you want to do, you will not be able to do. So what we should have here is our 2 power of n terms. That's coming from our complementary piece, and then we should have our particular solution then on the end, so that 2n plus 5. But we do need that particular solution in there for when we're doing simultaneous equations. If you try to do the simultaneous equation without that particular solution, you will get the wrong answer. Also bear in mind that power of n is outside the bracket. That's especially important if either root or both roots are negative. In this case, if you put the n inside the bracket, you're going to end up with the same answer because 3 is positive, but it will make a difference if it's negative. So just make sure you're getting in really good habits of writing that n outside your bracket. So example 2, let's solve a second order inhomogeneous difference equation, but this time we have an exponential particular function. So we're working with our exponential there on the right. Again, we have an example where this is already broken up, so we don't need to do that. So our first step is to focus on this piece here. This is an exponential and it doesn't have a constant, so we don't need to put one in. So that means we can write our f of n in the form of AB to the power of n. But remember that that base is the same as in the question. So that's going to be A2 to the power of n. That's really important because if you don't get your base at this point, you're going to have too many unknowns. So that base doesn't change. That's really, really important. So whatever base is given in the question, that's going to be the base that we're using for our particular solution. Okay, so we're working on the particular solution now at the moment. So again, just like before, let's do our f of n plus 1 over here. So that's a 2 to the power of n plus 1, and f of n plus 2, which is a 2 to the power of n plus 2. You want to do a little bit of cleanup on these. If you want to do it here, think of your rules of indice. That's going to be 2 to the power of n, 2 to the power of 1. So that's going to be 2a times 2 to the power of n. And f of n plus 2 can be broken up in the same way. So a 2 to the power of n plus 2, which is going to be a 2 to the power of n, 2 to the power of 2. So that's going to give us 4a times 2 to the power of n. So where we come along here, this is going to be 2 f of n plus 2 minus f of n plus 1 minus f of n, f of n equals 2 to the power of n. Remember that right-hand side doesn't change. So subbing that in, that's 2 times f of n plus 2. We just worked out it's 4a, 2 to the power of n. And then we have minus f of n plus 1, which is going to be 2a, 2 to the power of n. And then we have minus f of n, a, 2 to the power of n. And I'm actually going to put all these brackets outside here. We know it's not going to make a difference because 2 is positive. And it's going to equal 2 to the power of n. So you can see that there's a 2 to the power of n in all those terms. So I'm going to divide across by a 2 to the power of n, which gets rid of that, which allows us now just to focus on everything else, which is going to be 8a minus 2a minus a equals 1. So just be really, really careful. you do this division, it's going to leave 1 on this side. Okay, dividing will never leave us with a 0. Be really, really careful with that. So what that leaves us there is, that's 3, so that gives us 5a equals 1, so a is equal to 1 over 5. Or if you want to use decimals, that's 0.2. That means our function, f of n, is going to be 0.22 to the power of n. So that's our particular solution for this question. Okay, so now the hard bit's done, let's deal with the complementary solution. So the complementary solution, it's back to what we're used to. We're treating this left-hand side, so 2un plus 2 minus un plus 1 minus un equals 0 as x squared, 2x squared minus x minus 1 equals 0. So 2x x minus 1 plus 1 equals 0. And our roots are minus a half and x equals 1. Really take care with these because often students are rushing and get funny, silly answers for their roots. You want to make sure that part is good. So that's my alpha and that's my beta. This time our theorem that we're using is going to be Tn is equal to L alpha to the power of n plus beta plus m beta to the power of n. And this is going to give us our complementary solution. So L alpha, that's minus half to the power of n. This is a case where if you had that power in the wrong place, you're going to be in trouble. So if you had it inside the bracket, that's going to give us a different answer. So it's really important in this step that your power is outside the bracket. You're subbing in for A, for alpha and for beta. They go in brackets and that power is outside. So that's our complementary solution. And that means our final answer for un is going to be L minus a half to the power of n plus m 1 to the power of n plus 0.2 to the power of n. Now we have two things we want to test and to work with. So that's u0, so that's L minus a half to the power of 0 plus m 1 to the power of 0 plus 0.2 to the power of 0, and that will give us 2.2. So remember, anything to the power of 0 is 1, so that's giving me L plus m plus 0.2 equals 2.2, so that gives me L plus m equals 2, and that becomes equation 1. We're going to do the same thing with u1, so that's L minus half to the power of 1 plus m 1 to the power of 1 plus 0.2 to the power of 1, and that equals 0.9. So we can do that as minus 0.5 L plus m. So that's going to be plus 0.4, and that equals to 0.9. And actually, if I can clean that up, that's going to be just equal to 0.5, just because I have run out of space. So that's equation 1 and equation 2, and now we're going to need to solve those simultaneously. So let's solve these. Just bear in mind, it doesn't matter what order your alpha and beta is in when you're subbing into that complementary solution. So if you mix up your alpha and beta or yours is the opposite way to me, we're going to get different values for L and M. They're just going to be inverted. So my L will be your M and my M will be your L. So let's change some signs here. So that is giving me 1.5 L is equal to 1.5. So that gets us L equals 1. And since L plus M equals 2, that means M must equal 1. So let's go back and fill in our answers. So UN is equal to 1 minus a half to the power of n plus m, which is 1 to the power of n plus 0.2 to the power of n. That 2 to the power of n is its own little piece. It's not part of like a formula. We're not necessarily changing anything, so it can stay inside. It can go outside the bracket. It's not an issue. If you want to do some cleanup here, we can do that as minus 0.5 to the power of n. 1 to the power of n is just 1, so we can just do 1 plus 0.2, and then that's a 2 to the power of n. And that is our final answer for RUN. So example 3, we're going to solve a second order inhomogeneous difference equation, and this time we're looking at a constant particular function. So let's take a look here on the right hand side, and we see that this is a constant. Now this is actually one that often tricks students. So we have a function in the form f of n equals c. So remember, just let me jot this down. This is nothing to do with the question, but remember we had like we had bn plus c. Bn plus c. We talked about the n changing. So then when we come along and we do our f of n plus 1, it's now b of n plus 1. So it's the n is changing. So when we come along to a constant, students do very funny things. But actually, it's really, really simple. F of n plus 1 is still c. F of n plus 2 is also c. It's a constant. Constant means it's not changing. It doesn't have a variable. So it doesn't matter if we pick n plus 1 or n plus 2. There's no space for that n to go in. So therefore, nothing is changing. So this is actually so straightforward, but students often overcomplicate it. So be very, very clear about how you work with your constants. So we're working with the particular solution first. So the particular solution, we're looking at f of n plus 2 minus 2 f of n plus 1 minus 35 f of n equals 144. So that is going to be c minus, oh, I dropped my 2. Let me put it in up on the line above. So that should be f of n plus 2, and that should be minus 2 times fn plus 1. So that's minus 2c minus 35c equals 144. So that gives us minus 36c is equal to 144, and c then equals minus 144 divided by 36, and that gives us 4. So that's our function. F of n equals minus 4. Lovely and straightforward. We love to see a constant coming. However, it is something that often tricks students. You need to be very, very clear about the constant and how to deal with it. At this point, we have seen each of these types of particular functions appear on the exam with the inhomogeneous questions. So you really do need to be very clear on how to approach all of them. So let's put that up here. So we have f of n equals r minus 4. And now let's work with the complementary solution. So complementary solution, we're going to do x squared minus 2x minus 35 equals 0. That's x minus 7, x plus 5 equals 0, gives us x equals 7, and x equals minus 5. That's going to be my alpha and my beta. So we're using our different root theorem. So that is L alpha to the power of n plus m beta to the power of n. So our complementary solution here is L7 to the power of n plus m beta to the power of n. So when we come along and get our final solution, L7 to the power of n plus m minus 5 to the power of n plus the particular solution, which is a negative 4. So let's do our U0, U0. 0 plus m minus 5 to the power of 0 minus 4 equals 16. Remember, anything to the power of 0 is 1, so we get L plus m equals 20, and that's 1. So then we have U1, which is going to be L7 to the power of 1 plus m minus 5 to the power of 1 minus 4, and that equals 5. So that gives us 7L minus 5m, and that equals 9, and that becomes equation 2. So let's see if we have enough room to solve this. So for equation 1, I'm actually going to multiply it by 5, so we can work this through nice and quickly. So we have 7L minus 5m is equal to 9. And that gives us 12L minus 9. And unfortunately, sorry, I dropped my minus up here, which should have given me, instead of that, I should have had a minus 12. So that should be minus 60. And that gives us minus 51. So L gives us minus 51 over 12, which simplifies to minus 17 over 4. And then I'm going to go back to equation 1, L plus M equals minus 12. So my L minus 17 over 4 plus M equals minus 12. So working that through, I get minus 31 over 4 for my M. And then let's come back up here for our final answer. So UN is equal to L, which is minus 17 over 4, or you can write that in decimal if you prefer, 7 to the power of n, plus M, and M is minus 31 over 4, minus 5 to the power of n, minus 4. So that's our final answer for UN. So now let's solve a second order inhomogeneous difference equation where the particular solution is, or the particular function is quadratic. Now, this is one of, I'm not going to say the trickiest, but it's definitely one of the longest to work with. So let's see what happens. So we have a quadratic here. So this is one where it really would benefit you to do your function over here on the right. So f of n is in the form an squared plus bn plus c. So if we do f of n plus 1, that's going to be a n plus 1 squared plus b n plus 1 plus c, which is a n squared plus 2n plus 1 plus bn plus b plus c, which is an squared plus 2an plus a plus bn plus b plus c. Okay, so let's do our f of n plus 2 now. So that's a n plus 2 squared plus b n plus 2 plus c. So that is a n squared plus 4n plus 4 plus bn plus 2b plus c, which is an squared plus 4an plus 4a plus bn plus 2b plus c. So let's go ahead and work with our particular solution. So our particular solution is going to be f of n plus 2 minus 7f 7, f of n plus 1 plus 10 f of n equals 4n squared minus 10n minus 3. So that is an squared plus 4an plus 4a plus bn plus 2b plus c. That's just f of n plus 2. Then we have minus 7 by fn. So that's going to give me minus 7 an squared minus 14an minus 7a minus 7b n minus 7b minus 7c. And then we have plus 10 an squared plus 10bn plus 10c. And that should all equal 4n squared minus 10n minus 3. There is so much going on in this question. So we have an squared, an squared, an squared. I have an term, an an term. And I think that is it. I have a bn term. I have a bn term, and I have a bn term. I have c, 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 and then I also have some a's and some b's. So there's my a terms. And do I even have enough color? Let's use black. And I have a 2b and a minus 7b. There is so much going on here. So that gives us 4an squared. That's my red terms. I'm actually going to cross them as we use them so there's no confusion. We then have, I'm going to do the green ones next, 4n minus 14an, that's minus 10an. So they're gone. I'm going to do the blue ones next. So I have 11 bn minus 7 bn, so that's plus 4 bn. So that one's gone, that one's gone, and that one's gone. Crossing them out is a great trick because then if you do accidentally forget something, you will find it. So then we have minus 3a and minus 5b and then minus 6c. And that all equals 4n squared minus 10n. Doesn't look like minus 10n minus 3. So we want to break these up. So our n squared terms should equal our n squared terms. So that gives us a very nice little answer of just a is 1. Now you can show that. I'm just running out of space. So we have 4an squared equals 4n squared. So a must be 1. Then we can come around to our b's and we can see that, okay, the b's on the left, which are these ones, should equal this. Now remember a is 1. So we have minus 10n. So this is one we probably want to write down. So we have minus 10n plus 4bn is equal to minus 10n. So all the n's are gone. And actually that gives us b equals 0. And then our last one is, well, minus 3a, which is just minus 3, minus 5b, which is 0, minus 6c is equal to minus 3. So c is also equal to 0. So we're getting a is 1, which means that our function after all of that, f of n, is simply equal to n squared. So now let's deal with our complementary solution. Our complementary solution is going to work with our un plus 2 minus 7, un plus 1 plus 10 un equals 0. So that's going to be x squared minus 7x plus 10 equals 0. That's x minus 5, x minus 2 equals 0. So our roots are x equals 5 and x equals 2. That becomes my alpha and my beta, and I'm using my Tn. Oh, let me go with a slightly different color. Tn is equal to L alpha to the power of n plus m beta to the power of n. That means for us, for the complementary solution, it's L 5 to the power of n plus m 2 to the power of n. So to make our final solution for un, we pull our complementary piece and we add our particular piece, which is just n squared. So we do u0. u0 is L 5 to the power of 0 plus m 2 to the power of 0 plus 0 squared, which is gone, and that should all equal 2. That's L plus m equals 2, and that gives us equation number 1. We then can work with u1. So that's L 5 to the power of 1 plus m 2 to the power of 1 plus 1 squared, and that equals 8. So that is 5L plus 2m, and that equals 8. Take away 1, which is our 7. So that's equation 2. So if we work with equation 1 and 2 together, I'm going to multiply equation 1 by minus 2. So it's minus 2L minus 2m equals minus 4. So that's 5L plus 2m equals 7. M's gone, and I'm left with 3L is equal to 3. So L equals 1. Going back to equation 1, that means M equals 1. So for our final answer, we get un equals L, which is 1, and that's 5 to the power of n plus m, which again is 1, and it's 2 to the power of n plus n squared. Now, if you want to do some cleanup there, those ones are not actually required. So our final answer there is just 5 to the power of n plus 2 to the power of n plus n squared. These do get quicker the more you practice them. I think if you focus on getting that particular solution done first, getting really good at that, then this complementary solution piece we're quite used to from our homogeneous difference equations. So even if you're kind of short on time and want to really improve your progress here, I would focus on getting some practice questions and even just working through that particular piece to begin with, really getting on. Second thing the students, I suppose, do incorrectly is they tend to sub in that for U0 and U1 too early, they do it to where we have the Tn and they don't wait till their final solution. So just be very aware of that. So let's take a look at the 2025 higher level paper. This was question 10 part A. This is the first time we've been tested on inhomogeneous difference equations on their own. That means they weren't following a second order homogeneous question, they were a complete standalone question. So a new streaming media service is trying to increase its total number of customers. The company introduces a strategy to attract new customers. The company developed a difference equation to predict SN, the total number of customers in month end. The difference equation is S of n plus 2 is equal to a quarter S of n plus 1 plus 5Sn minus 15n plus 40, where n is greater than or equal to 0 and n is an integer. Immediately before the introduction of the new strategy, the company had 2016 customers, i.e. S0 is 2016. 1 month after the company has 3,500 customers, i.e. S1 is 3,500. So we have some important information there we don't want to lose. So it said write down values for S2 and S3. Now these are actually quite prone to error, so you just need to be really careful. So if we want to get S2, sorry, we'll do S2 first. Look at our formula. It's S of n plus 2. So that is S0 plus 2. That's what that effectively boils down to. And why I'm highlighting that is because that means n is 0. And that's going to be so important with our substitution, because you're going to come along and do S2 is equal to a quarter. The term before, so that's S1, so that's 3,500, no issues yet, plus 5 times the term before that, which is 2016. And this is where it went wrong for so many students. They were plugging the 2 in here, which is completely incorrect, because n is actually our 0. So you need to be very, very mindful of what n is. So when you work that through, that works out as 3,435. And then when we do the next one, S3 is S1 plus 2. So therefore, our n is equal to 1 when we do our substitution. So S3 is equal to a quarter of 3,435 plus 5 times, this is 3,500 minus 15 times 1 plus 40 into the calculator. And we get 5,258.75. So if you want to round that up, because we're talking about people, we're talking about customers, 5,259 customers. Equally, there's an argument there for rounding down, so you don't have that full number of customers, but we'll just do our normal rounding here. So next it's asking us to solve the difference equation. So we need to do a little bit of work here. First thing is, okay, let's write this down. So that quarter, we want to get rid of it. So really focus on bringing it over, but also dealing with anything that doesn't already have a quarter involved. So we're multiplying that side by 4. We multiply here by 4, but don't forget you're also doing this by 4. So what that means is we get 4 Sn plus 2 is equal to, that's gone, Sn plus 1 plus 5 Sn, but we still have minus 60n plus 160. So just be careful not to forget to multiply those last two. Sometimes our fractions, we're so quick to like bring the bottom line across the equals, we forget about actually really what we're doing is we're multiplying everything, but well, both sides by 4. And if we multiply both sides by 4, part of the right hand side has a quarter, but part of it doesn't. So in order to make this look the way we wanted, we want to move our Sn terms over to one side. That gives me minus 60n plus 160. As soon as we're here, we can now clearly see that we have a linear. Okay, so that means if we're dealing with our particular solution, our f of n is going to be in the form bn plus c. If we want to do our f of n plus 1, that's going to be bn plus 1 plus c, which is bn plus b plus c. And if we want to do f of n plus 2, it's going to be b n plus 2 plus c, which is bn plus 2b plus c. Okay, I've just given us a bit of space so we can work through. Let's get our particular solution. So this is going to be 4f of n plus 2 minus f of n plus 1 minus 5 f of n plus minus 60n plus 160. So we add in bn plus 2b plus c minus bn plus b plus c minus 5 bn plus c plus minus 60n plus 160. So that's 4bn plus 8b plus 4c minus bn minus b minus c minus 5bn minus 5c plus minus 60n plus 160. So if we want to do a bit of cleanup here, there's a bn term, a bn term, and a bn term. So that's minus 2bn. Here we have a b term and a b term. So that's plus 7b. And then we have these c terms. So that's minus 2c. And that all equals minus 60n plus 160. So let's focus on the n terms first. Remember, what we have here is an identity, so our focus is not on the ends, our focus is on combining those unknown coefficients. So we split them into the types of terms we have. So the minus 2bn, the n term on the left, should equal minus 60n, the n term on the right. We ignore n, and then we get b equals 30. We then want to look at our non-n terms. So they are effectively our constants. Call them constants if you're happy to do that. So that's anything without an n. Sometimes in the middle of an exam or when you're kind of thinking about 100 other things, it can be really nice to take the idea of a constant out and just say anything that doesn't have an n, we're now including. So we have 7 by 30 minus 2c is equal to 160. That's minus 2c is 160 minus 210. So that's minus 50. And c is going to equal R25. So what that means for us is our particular solution is f of n equals 30n plus 25. So now we need to think about our complementary solution. So now let's think about our complementary solution. So we're dealing with this left-hand side, Sn plus 1 minus 5 Sn equals 0. So we're treating it as a homogeneous difference equation. And we get 4x squared minus x minus 5 equals 0. 4x minus 5, x plus 1 equals 0. So x is equal to 5 over 4 or 1.25, whichever way you want to work with it. And x equals minus 1. So in terms of our theorem, we have two distinct roots. So we're using our different root theorem, which is L alpha to the power of n plus m beta power of n at Tn is equal to L 1.25 to the power of n plus m minus 1 to the power of n. So when we come along for our final answer for Sn, it's going to be our L 1.25 to the power of n plus m minus 1 to the power of n. Plus, don't forget, we already have our Fn. I should have pulled that up from us before. So that is 30n plus 25. So we're going to pop that here at the end. Plus 30n plus 25. And there was also two little bits of information that we needed to remember. So that was S0 was 2016 and S1 worked out as 3,500. So we'll need that to do our substitution here. So S0 is going to be L 1.25 power of 0 plus m minus 1 to the power of 0 plus 30 times 0 plus 25, and that all equals 2016. So we get L plus M plus 25 equals 2016. So that gives us L plus M equals 1991, and that becomes equation 1. We then have S1. S1 is L 1.25 to the power of 1 plus M minus 1 to the power of 1 plus 30 times 1 plus 25, and that's going to equal our 3,500. So that gives us 1.25 L minus M plus 55. So let's go straight to this. So 3,445. So we have, 3,500 minus 55, and that's equation 2. And let's work through that simultaneously. So I don't think I'll have enough room, but let's just start it here to begin with at least. So 1.25 L minus M equals 3,445. That disappears. We get 2.25 L. That's 5,436. So L is that divided by 2.25, and that gives us 2,416. So M is going to give us minus 425. And I'm going to go back up here to give our final answer. So Sn is equal to L, which is 2,416 times 1.25 to the power of n plus m, so minus 425 minus 1 to the power of n plus 30n plus 25. So that's our lovely final answer. So part 3 then asks, the strategy is deemed successful if the service has at least 35,000 customers after 1 year. Is the strategy successful? Justify your answer. So 1 year, that means 12 months. Remember, N is months in this case. So let's sub that in. So 1.25, we don't have to worry too much about substitution like we did for part 1, because everything is our N, and our N is our 12 in this case. So it's only when we're subbing into the original that recurrence relation that we have to be really, really careful. So let's plug that in. That gives us an answer. Oh, it's not euros, so it's 35,117. So don't forget to answer the question, is the strategy successful? So the answer is yes, because the number we got, so that's 35,117, is bigger than the 35,000. That is the threshold to be deemed successful. So, for example, for our last example in this video, we're going to look at the 2023 higher level paper, and it's question 6. So this format of second order difference equations has been the same on the sample paper, the 2023 paper, the 2023 deferred, and the 2024. So we get a full question on second order difference equations. And the first half is an homogeneous difference equation. And then we get in the second half a related non-homogeneous difference equation. And it's really important that you understand in these questions what elements of the homogeneous difference equation you can pull through to the second part and what needs to change. So we're going to work through this first half, this homogeneous piece first, and then we'll link it to our non-homogeneous. So we have spider plants that can reproduce asexually, producing new plants called spiderettes or pups. The manager of a garden centre is told that a 1-year-old spider plant produces 2 pups each year, that a 2-year-old spider plant produces 3 pups each year, and a spider plant and that spider plants which are less than 1 year old or more than 2 years old do not produce any pups. The manager predicts that the number of pups produced in the garden centre in any year can be expressed by the second order homogeneous difference equation un plus 2 equals 2 un plus 1 plus 3 un, where n is greater than or equal to 0, n is an integer, and we get u1 and u0 equals 1 and u1 equals 2. So there's a lot of reading there, but our focus is going to simply be on the difference equation. So the first thing they ask us is to write down the values of u2 and u3. So u2, using this difference equation, is 2 times our previous term, which is u1, plus 3 times u0, which is 2 terms before it. So that's 4 and 3, that gives us 7. u3 is 2 times the previous term, which we've just worked out to be 7, and 3 times 2 terms before it. For that, that's going to be u1, which is 2. So that's 14 and 6, and that gives us 20. So the next part asks us to solve the difference equation to find an expression for un in terms of n. So getting rid of anything that really isn't relevant and simply leaving our difference equation, we have un plus 2 is equal to 2 un plus 1 plus 3 un. What that means is we can create the corresponding characteristic quadratic equation, which is x squared equals 2x plus 3. So bringing everything over, x squared minus 2x minus 3 equals 0. That's going to give us x minus 3, x plus 1, and we get 2 roots, which are x equals 3 and x equals minus 1. So because we have 2 different roots, we're going to call those alpha and beta, and we're going to use the different root theorem, which is Tn equals L alpha to the power of n plus m beta to the power of n. So for us, that's un equals L 3 to the power of n plus m minus 1 to the power of n. Now we're going to do some substitution. We've been told in the question u0 is 1 and u1 is 2. So our first substitution is to write out our u0. L 3 to the power of 0 plus m minus 1 to the power of 0, and that should give us 1. So that's L plus m equals 1. u1 is L 3 to the power of 1 plus m minus 1 to the power of 1, and that should give us 2. So that's 3L minus m equals 2. So working with these two simultaneous equations, we'll put one over the other. The m straight away disappear. We get 4L equals 3. So L is equal to 3 over 4, or 0.75 if you want to leave it in decimal. L plus m equals 1. So m is equal to 1. Take away our 3/4. So m is equal to 1/4. So that gives us our final answer of un equals L 3 over 4, 3 to the power of n plus m 1/4 minus 1 to the power of n. So solving the homogeneous is much quicker than the non-homogeneous we've been looking at in this video, but there are elements in this part that we'll be able to bring forward with us. So now that we have the answer to un, we're going to find u10. So that is in, everywhere there's an n, we're subbing in 10. So 3 over 4, 3 to the power of 10 plus 1/4 minus 1 to the power of 10. Make sure that power 10 is outside of the bracket, especially on that minus 1. So that gives us 44,287. So now we move on to the non-homogeneous section of the question. So the manager realizes that this model does not take into account the sale of any spider plants produced in the garden centre. The manager decides that the garden centre will not sell any of the spider plants in either of their first 2 years, but that 2n of the new pups will be sold in each year n after that. Now that's quite complicated, but luckily for us, they give us straight away the actual difference equation. So as part of the improved model, the manager now predicts V, the number of pups produced and retained, not sold, in the garden centre in any year can be expressed by the second order inhomogeneous difference equation Vn plus 2 equals 2 Vn plus 1 plus 3 Vn minus 2 n plus 2, where n is greater than or equal to 0, n is an integer, v0 equals 1 and v1 equals 2. solve this new difference equation to find an expression for Vn in terms of n, and then calculate V10. Okay, so giving ourselves a bit more space to solve it, step 1 for solving these non-homogeneous difference equations is to separate out all the v's on one side. So I'll bring over the minus 2vn plus 1 minus 3vn, and that equals minus 2. I'm going to multiply this out at the same time, minus 2n minus 4. Be careful with that. So then the second thing we're going to do is find the particular solution. So we need to look at the right hand side and make a decision about what type of function it is. So this part here, we can see it's a linear function, which means we're going to get an answer that's in the form f of n equals bn plus c. So we're going to change our v's on the left hand side into functions. So that is f of n plus 2 minus 2 f of n plus 1 minus 3 f of n, and that's all going to equal, the right hand side stays the same, minus 2n minus 4. So that gives us b n plus 2 plus c minus 2 bn plus 1 plus c minus 3 bn plus c. That's minus 2n minus 4. So expanding that, we get bn plus 2b plus c minus 2bn minus 2 minus 2c. So, sorry, we have minus 2bn minus 2b minus 2c minus 3bn minus 3c equals minus 2n minus 4. So at this point we have an identity. You can tidy up here if you like. I'm just going to focus on our two types of terms. So we have n terms and we have our non-n terms, so our constants. So we have all of our n terms highlighted, and then we have our constants, so our non-n terms. And the n terms on the left are going to equal the n terms on the right, and the constants on the left are going to equal the constants on the right. So our n terms. So we get bn minus 2bn minus 3bn equals minus 2n. And each of these has an n term, so we can either ignore the n, you can think of that as divide across, but we can simply focus on the coefficients. So I have b minus 2b minus 3b, that gives me minus 4b equals minus 2. So that gives us b equals 2.5. So then we're going to look at the constants, or the non-n terms. So the non-n terms are 2b plus c minus 2b minus 2c minus 3c equals minus 4. So we have 2b minus 2b, that'll give us a 0. We don't even need to sub in our previous answer for b, so we end up with minus 4c equals minus 4, so c equals 1. So in terms of our function, we get f of n is equal to 1/2 n plus 1. Now we can do a little bit of tidy up on this. So we can actually write this as a single fraction. So the half n can be written as n plus 2, and instead of 1 we can write that as 2 over 2, and then we can combine that into n plus 2 over 2. It's absolutely fine to leave your answer the way it was. This just might be a little bit neater when we're working.